Swayam Prabha. Digital India. Educated India.
This presentation is an identification case study, and the term STH stands for a stirred tank heater. This is a pilot scale heater in our laboratory at the University of Alberta. So I'm going to share with you a very simple identification case study using pilot scale data. So just to recall, what do we mean by identification? Given some input time series data into a process and also the output time series data for the process. So the input time series data is as shown here, u of t. The output time series data is y of t. In this case, the input is the steam flow rate into the process. The output is the temperature of the fluid in the stir tank heater. Given the input-output time series, the question to ask is, given the input data and the output data, can we obtain a model of this process? Remember, the processes are generally quite high order, so system identification is an exercise in model reduction. Processes are theoretically very high dimensional. Identification provides a good reduced complexity model of the process. The basic idea in identification is the following. Given the input data sequence and the output data sequence, can we generate some parameters such that the sum of the squares of the errors between the measured output and the predicted output is minimized. So we are saying sum of the squares of the error is as small as possible. This is known as the least squares identification procedure. So mathematically the idea is, can we map this data using some ID function into parameters that will very likely fit the process curves. Okay, so we are going to apply this idea to this pilot scale computer interface process. The process input is the valve adjustment on the steam line. The output is the exit temperature that is measured here. So the steam enters this stir tank heater and it goes through a steam coil to warm the water. We're feeding in cold and hot water into this tank. The level of the tank is well controlled, and we're measuring the exit temperature at several locations. At thermocouple number 1, number 2 here, number 3, and number 4. Okay. So the data streams that we have is the process input, the valve position, and the process output, which is the output of the thermocouple. And here is a plot of the output and the input. This is obtained using the function ID plot in MATLAB. The data can be available to people who would like to use do this identification exercise, and it is in a file called STHID.txt. It only consists of two columns, the output data and the input data. The data is stored at each sample interval in time, and I believe the sample time is 4 seconds. So here is the output stream, here is the input stream. The input stream is a very simple random binary sequence. The mean value of the output is about 35 degrees, and the mean value of the input is 30%. So the 30% val position. So the first thing you have to do is detrend the data. You have to zero min center the data, and that can be done using the function detrend in MATLAB. This function may have changed, so just check, or it could be detrend. And there may be more parameters to choose for this function. So if you detrend the data and plot the data, in the detrended data is now labeled as ZD. Here is the plot of the detrended data. So we feed in this input excitation stream into our SysID algorithm, and the output stream into this ID algorithm to see what to do, what to get. Now before we look at the identification steps, let's analyze the function CRA. CRA stands for correlation analysis, or correlation and spectral analysis. So with a slightly different notation, consider the following sample data system with an infinite order impulse response coefficient. So we say y of t is equal to g naught times ut plus g1 times ut minus 1 plus g2 times ut minus 2, etc., etc. This is an infinite order impulse response term on the right hand side. How do we get gk? If you were to divide the numerator bz minus 1 by the denominator az minus 1, you will get an infinite order impulse response terms, and that's what gk terms are. So consider a sample data system with impulse response coefficient g sub k. Let ut be a signal that is the realization of a stochastic process with zero mean value. So the random binary sequence or the pseudo-random binary sequence that we've generated in the examples in the previous slides would satisfy this criteria. And the covariance function of the input is r sub u. Assume that u and v are uncorrelated. This term v is the noise, random white noise, and u and v are uncorrelated. So the cross variance function between u and y is then, if we multiply both sides of the previous equation, let's go back, if I multiply both sides by u and then take the covariance function, this is what we would get. So the expectation of yt times ut minus tau, the expectation operator is essentially an infinite order sum operator. So the covariance of y and u with a time lag of tau is denoted by this term here. We multiply everything by ut minus tau and apply the expectation operator. It turns out, because v and u are uncorrelated, this term becomes 0, and all we have is these terms here. So ru tau minus k is the cross covariance between the output and the input with lag k. If the input is white noise, then Ru by itself is equal to a non-zero value at tau equals to k, and for all other tau not equal to k, it is equal to 0. So therefore, when you apply this white noise input, this term becomes simply lambda times g tau at the time lag of tau. So the cross covariance function between the output and the input will therefore be proportional to the impulse response coefficient. This function can be easily estimated using the function CRA in MATLAB. So the function CRA does the following. You collect the data yk, uk, you zero mean center the data that we've already done, you form signals LQ times Y tilde Q and UF L times U tilde. This is to zero mean center, to whiten the input if it is already not whitened. That's what the filter L does. And then form the estimates, the covariance between Y and U with lag tau is this term here, and from the expression that we had previously, this expression, G of tau is RYU tau divided by lambda, and that's what we are doing here. We compute the covariance function between the input and output with lag tau divided by lambda, and lambda n is computed from the input that you provide. So the function CRA does all of this, and here is the output. We applied the function CRA on the data set ZD. ZD was the D-trended data set, and we get these series of impulse response coefficient. And the utility of function CRA in getting this is to determine if there is any delay in the input, and it turns out yes, there is at least a delay of 5 or 6 sample intervals, because these impulse response coefficients are well within the confidence bounds on the estimates of the impulse responses. So this will tell us that the delay is very likely 6 sample intervals, and so to determine is it 5 or 6 sample intervals, we obtain various parameters of the system using the ARCS model. You will recall the ARCS model is AY equals to BU times U plus the noise term. So the input to the ARCS model is the testing parameter, the training parameter, the validation parameter. In our case, because the data set that we have is not very large, we're using the same set of data for validation as well. Ideally, you would like this data set to be different. It has to be detrended, but it should be different from the training data set. We don't have that luxury here because the data set is quite small. And we are doing this for NN, which is 2, 2, and then the delay is roughly assumed to be at least 4 to 8 sample periods. Okay, so we've defined, I believe we did define NN earlier, or not defined, but NN is 2, 2, 4 to 8. So what we get using, if we list the argument for V or the output for V, We get the loss function, sum of the squares of the coefficients, and the order of A. The order of A is always A. The order of B is also A, also 2. So the order of A and B remains the same, and here is the delay. So for a second order A, second order B, and a delay of 4, the loss function is 0.0086. For a fifth order delay, for a delay of 5 sample periods, second order A, second order B, the loss function is 0.004, and then a delay of 6, the loss function goes down even more, half of this amount, 0.0026. Thereafter doesn't change very much. So it turns out very likely the delay in the process that we have is 6. Here is the loss function. So knowing that the delay is 6 sample intervals, now we want to explore what is the order of the A and B, what is the order of the A and B polynomials. So we use the function struct again, where the A polynomials can be of any order between 1, 2, and 3. The B polynomial can also be of any order 1, 2, and 3. The delay now is fixed at 6. So altogether we are going to estimate 9 different models. Here is the A polynomial order, here is the B polynomial order, A, B, and here is the loss function, and the delay remains fixed at 6 intervals. And what you find out is either the lowest loss function is either this or this or this. So one could easily say our process is second order. We have a second order A polynomial, a second order B polynomial with a delay of 6, or a second order A polynomial and a third order B polynomial with a delay of 6. There isn't too much of a choice between these two loss functions. It is likely that the delay is not an exact integer multiple of the sample time. So it could be between 6 and 7 sample periods, or it could be 6 point something, which may be the reason why you end up having a third order B polynomial. But either one of these should suffice. So let's check this out. So we plot the loss function, and it turns out the loss function is at its lowest value either here with 4 parameters or at most 5 parameters. So the details of the estimated model is, here is the estimated A polynomial. So the coefficient that are estimated is 1 minus 1.305 to the power z to the minus 1, and here is the standard deviation, plus minus 1 standard deviation on this estimate. The second coefficient is 0.3674 with the corresponding standard deviation. And here is the second order B polynomial, 0.5629 with this very small standard deviation, and then another term, second B term, with the corresponding standard deviation. So the parameters that we've selected is second order A, second order B, delay of 6. And this is the additional output that we get from the arcs function, and when we ask it to present the model type. Okay, so the arc structure is as shown here. The second order polynomial, the second order process would be this process, and we can also write this in the following form. Yt is a1 yt minus 1 plus a2 yt minus 2. So these are the two autoregressive terms. These are the two exogenous input terms, b1 ut minus 6 and b2 ut minus 7 plus e of t. Okay. And the noise is zero mean white noise with the standard deviation of sigma squared. Now, just want to point out, when you measure something, so here is the flow rate that we measured, here is the temperature that we measured in another pilot scale equipment, and while the temperature appears to be more or less constant, we look at the sensor noise or the fluid noise. So this is normally distributed and the error is approximately 0. Same thing here. Now there was a slight issue with this sensor here, and that was related to quantization of this thermocouple. So sensor noise is random with 0 mean and normally distributed. It is normally distributed like white noise. So how do we monitor or how do we validate the accuracy of the model that we've identified? The way to do this is to use the function resid. The most common use of the function resid is to validate the quality of the identified model. We do this by analyzing the residual correlation for the given validation data set. So we feed the input sequence into the same process, we feed the input to the model, we compare the measured output with the predicted output and compute the errors, the residual errors. What the whiteness test says is the autocorrelation of the residuals must be insignificant. That is within the 99% confidence bound for all 0 legs. They should be 0 mean and be within the 99% confidence bounds for all non-zero legs. Ideally, residuals should be like white noise. And the other important test is that if the residuals are white, then naturally the correlation between the input and the residual will be 0. And to check for that independence, you look at the cross correlation between the input and the residuals, and it must also be insignificant for all the legs. So the saying here is you should have squeezed out every bit of information that you can get from the input excitation into this process and include that in the model, with the results that the correlation between the input and the residual should be insignificant for all legs. Let's check this out. So here is an example. This is the serial dependence of white noise at different legs. So we are plotting ui versus ui plus phi. There is no apparent relationship between the input at one time and the input at 5 sample intervals later. Here is another case. The plot of noise ui versus ui plus 15. Again, very random. So there is no apparent correlation between these two inputs. And that's the case with white noise. So for the data that we had, so this is an example. We generate random white noise of length 1001, and we look at the X correlation for 20 legs for this noise term. So here are the 20 legs. Here is the correlation coefficient, and the correlation coefficient is of course perfect 1 at leg 0, but for everywhere else it is 0. It is within the confidence bound. To check if the residuals are right, obtain its autocorrelation using the X-score or the resid function. These functions may have changed names, so just be careful, but look for equivalent functions in MATLAB if that's what you're using. If you're using Python, there must be equivalent functions in Python. So here is the correlation between the output of between the input and the residual error. And what you have here is the cross correlation between the input and the residual, and it is non-zero for lags -1 and +1 roughly, or -2 and +2, but the autocorrelation of the residual is almost like white noise. And for the 2-3-6 model, we do have a slightly better autocorrelation for the residual. And of course, in both cases, the cross correlation is 0. So let's look at the result. If we superimpose the predicted output on the measured output, you can barely tell the difference, except somewhat here. I don't know again what happened. And here is the plot of the measured output versus the predicted output. And everything fits perfectly, more or less, on this 45-degree line. So this concludes that the model that we've obtained is very good. Ideally, this exercise should have been done with a lot more data set, where you have used different data sets for training and then applied the model to the separate validation data set. That wasn't the option for us, because we only had less than 300 points to carry out this identification. So the script file for this case study is given here. You can easily copy this and run this in a MATLAB program, and you would get all the outputs that I've shared with you in the slides. It is a good idea for you to play around with different parameters and see what kind of a model you get. But I hope this case study will help you to learn about the application of identification methods on real data, and it'll help you in identifying models for the processes that you may already have data, for which you will have the data, and therefore you will be able to obtain a model. Thank you.